Hi and welcome to this video which is covering the complex number mock exam questions. So with complex numbers we are limited to one question, or have at least to this point been limited to one question per year, all in section A, so a 25-mark question. And this means that we've a very limited set of resources to work with. So coming and looking at the mock question is a great way to really get some extra practice. Question 1, so this is a full 25 marker. Z1 is equal to A all over 1 plus I, and Z2 is B over 1 plus 2I, where A and B are elements of the real numbers, and I squared is equal to minus 1. So these are two complex numbers, and they said given that Z1 plus Z2 equals 2, find the value of A and the value of B. So this is very much just an algebra style question. So hopefully no difficulty with it. We are given Z1 plus Z2 is equal to 2. So we get A all over 1 plus I plus B over 1 plus 2I, and that should all equal 2. So just like in any algebra question that has fractions, we're going to try to get rid of the fractions. We get rid of the fractions by multiplying across by the lowest common denominator, which is going to be both denominators multiplied together. So 1 plus 2I, and don't forget to multiply both sides of the equal. So 1 plus I, 1 plus 2I. So we get so lovely cancelling here. That gets rid of the fractions, that was the point. And we get A bracket 1 plus 2I plus B bracket 1 plus I equals, I'm going to multiply the 2 in, so 2 plus 2I, and that still needs to be multiplied by 1 plus 2I. So we get A plus 2AI plus B plus BI, and that equals, when we multiply this, we get 2 bracket 1 plus 2I plus 2I bracket 1 plus 2I. I'm going to work down a little bit, so we get 2 plus 4I plus 2I plus 4I squared, and that gives us 2 minus 4, so that's subbing in for the I squared, plus 6I, which is minus 2 plus 6I, and that gives us exactly the same as what we had, 2AI plus B plus BI. So that's exactly the same. So what we're going to do is we're going to use the same method we would for identities when we're in algebra, but we're going to equate the real numbers on the left to the real numbers on the right, and then we're going to equate the imaginary numbers on the left to the imaginary numbers on the right, and that should give us all the information we need to solve for A and B. So let's deal with the real numbers first. So the real, and with the real we get A plus B, and that equals minus 2. We then look at the imaginary, and for the imaginary we have 2AI plus BI equals 6I. Now the i's can be ignored or cancelled or divided, whatever way you want to think of it, and we get 2A plus B equals 6. So what we have now are two equations, so we're going to work with them together. We have simultaneous equations, and we're going to figure out what the value of A and B is. So A plus B equals minus 2. 2A plus B equals 6. I'm going to just change the signs of the top equation. So that's plus. That will eliminate the B's, and we get A equals 8. And I'm going to take either equation, I'm going to take one, and that's A plus B equals minus 2, but A is 8 plus B equals minus 2, so B equals minus 10. So they are our two answers. So nice and straightforward, nothing very difficult, very much using the I as we would any other variable like we would in algebra. The only difference here is that the I has a specific value of minus, or the square root of -1. So the second part of this question tells us that U is a complex number with a modulus 8 and an argument 2 pi over 3. And B is here given in rectangular form 2 root 3 minus 2i. So they want us to write both these in polar form. Now, just some things to note. They've given us that theta is between 0 and 2 pi. So they've specified here that they want radians and they want positive radians. So negative angles wouldn't technically be allowed because of the way that they've structured this, but remember this is a mock question. U is quite straightforward to do because they've given us the pieces we need. So modulus is or, and argument is theta, so we get 8 cos of 2 pi over 3 plus I sine 2 pi over 3. So that is simply just putting it in, not even to what we know as polar form, because they've actually given us polar form. They've been very nice in this question. The second, so the second complex number we want to work with is V. Now, V they've given us in rectangular form, so we're going to have to go through our usual steps to get that into polar form. So the first step is to sketch it out. So we have 2 root 3 minus 2i. So we draw our argon diagram and we're going to sketch out where that would be. So we will be talking about down here. That is where V is. And this would be the imaginary part, that's 2, and this is 2 root 3. We would talk about this angle here being our reference angle A. So that is the small acute angle, like we would when we're talking trigonometry. But the actual argument that we want is that big angle there. So we can kind of now see from this sketch, if I can work out A, how we would then work out theta. So this is opposite and this is adjacent. So we have everything in that we need. The first thing that I will always do is I'll actually work out the modulus, and we don't really need the sketch for the modulus, but it would always be what I would consider the first step. So that's or, which is another way to say the modulus of V, and it's the square root of, we say a squared plus b squared, so it's the real part squared plus, and it's the imaginary coefficient, so you don't put the I in because that will change things. So we have 4 times 3, that's 12, plus 4 is 16, so that gives us a modulus of 4. So the second thing we're going to work out is our argument. So based on that diagram, we're going to use the tan of A, the reference angle. So we're not at the argument yet, we're just at that reference angle, is opposite over adjacent, and that simplifies 1 over root 3. So log tables page 13 I always think is just the easiest place to work with this, because by the time you get your calculator and you type all this in, if you page 13 open in front of you, you can just glance down at the page and we know that that's 30 degrees. However, we're actually in radians today, so we're pi over 6. Now if you're really struggling with the radians still, you can put the degrees in beside it. So that kind of helps you as you work through. So that's A, but actually we want theta. So if I want the argument, I would say that that's 360 minus what we have, which is 30 degrees. But again, that's in degrees. That would give me 330. But if I wanted then to work in radians, 360 is 2 pi minus pi over 6. And cleaning that up, that gives me 11 pi over 6. So that gives us V as 4 cos of 11 pi over 6. My 11 turned into a pi. 11 pi over 6 plus I sine 11 pi over 6. So that's our U and that's our V. So part 2, use de Moivre's theorem to evaluate U divided by V all to the power of 6. So I've just pulled in U and V from our previous question. And just to save rewriting it, effectively what we're being asked is to take the two of these, divide them and put that to the power of 6. So I'm going to take these two, divide them and put this to the power of 6. So we have a shortcut for division. Shortcut is super handy. That shortcut only works when they're in polar form. If they were in rectangular form, we have division, we would have effectively what would be like rationalizing the denominator, so multiplying the top and the bottom by the conjugate of the bottom. So it becomes quite tedious with the multiplication. So if it is in polar form, it's so nice to use this shortcut. So the shortcut, so u divided by v all to the power of 6, is you simply divide the modulus of u by the modulus of v, so 8 divided by 4, that gives us 2. And then we subtract the angles. So we have a shortcut for multiplication that's effectively the opposite, but what we get here is the cos of 2 pi over 3 minus 11 pi over 6, and then that's plus I sine 2 pi over 3 minus 11 pi over 6, and we are still doing that all to the power of 6. So you can clean that up further, and I will. So that gives us 2 cos of, and we get into negative angles here. Now do bear in mind that this is a mock question, but I'm not going to panic too much about these negative angles, and hopefully everyone is aware that negative angles are just measured in a different way. So a negative in maths is usually got to do with going another direction. So for us, we measure our angles anti-clockwise. So when we see a negative angle, that's just an angle that has been measured going clockwise. So they're not anything scary or anything like that. I'm actually going to ignore the fact that it's a negative angle. You could convert them, but because they've asked us to evaluate u over v, and evaluate means find a value, and that doesn't scream to me polar form. That tells me we're going to get just a number answer. So we're not going to leave those angles there. So there's no need to convert. The calculator will do a lot of that work for us. So I'm going to apply de Moivre's theorem now, that power of 6. So you can use page 20 to help. So that gives us 2 to the power of 6 cos, and you're multiplying it, 6. And like that is where our shortcut comes from. So effectively, if you were adding that angle 6 times, it's 6 times that angle. So like this is a version of that shortcut for multiplication. So we have 6 times minus 7 pi over 6. And we get a little bit of cleanup. So the 6's cancel. So 2 to the power of 6, that's 64. And then we get the cos of minus 7 pi plus I sine minus 7 pi. Now, there's lots that you can do to work with this. So we can think of that as we are going, like I said, clockwise, and we're doing that 7 pi. We know each rotation is 360 degrees, which is 2 pi. So actually that brings us back to just a negative pi. Pi is 180 degrees, so if I rotate anti-clockwise 180 degrees, it's the same as clockwise 180 degrees, because 180 degrees is halfway. But you don't even have to think about all that, because if you have your calculator in radian mode, you should be able to go straight to your calculator and work it. I'm going to do it just over here for a bit of space. So we're doing u over v to the power of 6. So you can do, I would generally put in the calculator 64 cos over minus 7 pi. Again, double check you're in radians. Plus I, you can't put that in the calculator. Oh. So, sorry. So you can't put the I part into the calculator. But you can have 64 sine of minus 7 pi. So that should be able to go into the calculator, and what that gives us is minus 64, and then that gives us a 0i. So they've said evaluate, so they didn't say rectangular form or anything like that, so we can simply leave it as minus 64. So there's a lot more you can do with the negative angles, but I suppose if you're not giving your answer in polar form, there's no need. Even in polar form, negative angles are generally accepted. We have seen like a mock question that specifies that it should be between 0 and 2 pi, but negative angles are absolutely fine. And I suppose although we talk about bringing it back to an angle under 360 degrees or 2 pi if you're talking radians, if your answer is not going to be given in polar form, so if there's no angle in your answer, you can literally just go and work with the angle that you have. Makes life a little bit easier. So question 2, this is a full 25 mark question. So part A says 2 minus I is a root of this equation where k is an element of the real numbers. Find the value of k. So we're told that this is a root, which means that when we sub it in, we know we will balance that equation, so that will be equal to 0. So our roots when we're in complex numbers is z. We know that because if you look at your equation, the equation has z's instead of x's. So I'm going to sub this in. So 2 minus I cubed minus k times 2 minus I squared plus 21 times 2 minus, 21, 2 minus I, and minus 20, and that should equal 0. So we have a little bit of work to do. It's not lovely. We have a bit of cubing going on. For cubing, I'd suggest that you multiply the bracket by the square of the bracket. So square the first, twice the first by the second, square the last. So it's just the easiest way to do it. And then we have another square bracket here. I'd suggest that you multiply this again and double check your answer, because this will catch if anything goes wrong. And multiplying this out, we get 42 minus 21, 21i minus 20 equals 0. So I'm going to do a little bit of cleanup. Remember, I squared is equal to minus 1. So this is actually 2 minus I times, that's 4 minus 1, so that's 3 minus 4i. So always do that cleanup just to make your life a little bit easier with the multiplication. So this is 3 minus 4i as well. And a little bit of cleanup here gives us 22 minus 21i, and that should equal 0. Doing a bit of multiplication, I'm going to split my bracket. Minus I, 3 minus 4i, minus 3k plus 4ki plus 22 minus 21i, and that should equal 0. That gives us 6 minus 8i minus 3i plus 4i squared minus 3k plus 4ki plus 22 minus 21i equals 0. And we're going to do a little bit of cleanup. Now it's quite long, so I'm going to take out my highlighter for this. So I have 6, and I'm going to add this because that is actually minus 4 when I sub in the I squared. And I have a 22 here to add to it. And then for the imaginary numbers, I have minus 8i, minus 3i, minus 21i. So that's 32, right. I'm ignoring the terms that have k's in them, and I've done that on purpose. But what we get is 6 minus 4 plus 22, that's 24. And then I have a minus 3k, there, that's the real part. And then I have minus 8i minus 3i, that's minus 11, minus 22, so that's minus 32i plus 4ki, and that should all equal 0. So what we can do is we can look at the real parts and we can look at the imaginary parts. And when we do that, we should be able to work out what k is. So in the real parts, we have 24 minus 3k equals 0. So therefore 3k equals 24. So k equals 8. So actually we don't need the imaginary bit. But if you had decided to use the imaginary bit instead, 32i plus 4ki, and that should again equal 0. Ignoring your i's, we get 4k equals 32. So k equals 8, both give exactly the same answer. But in this case, we were only required to use one. We only needed the real or the imaginary parts to do that. So part 2 then tells us that 2 minus I is a root of this equation, and they want us to find the other two roots. So we know that z, one of the roots is 2 minus I. Because all the coefficients of that equation are real, we actually know then the conjugate root theorem exists, which is 2 plus I. So that basically means in order to get those numbers as real coefficients and a constant there at the end at minus 20, the conjugate must also be used. So effectively I have two roots, and what you could do is go, and I'll kind of write this out. We've done it a few times, but it's not particularly nice. So you have roots, you change it to a factor, and then you multiply them together. But when you change them to factors, what you get is z minus 2 plus I times z minus 2 minus I, and it's just not very nice because it's 3 by 3. Now you'll get there. There's nothing wrong with that, but it's quite a long method. So a better method that we would generally use is a shortcut to basically getting to the quadratic. So getting to the answer of these factors multiplied together. And the shortcut is z squared minus sum of the roots z plus product of the roots, and that equals 0. So we're going to need to get the sum, which is 2 minus I plus 2 plus I, which is just 4, and then the product, which is 2 minus I, 2 plus I. Now we have a difference of 2 squares answer here, so we can work backwards from that shortcut and simply square the first minus square the last. Minus, now just be careful, that's minus 1, which is a plus, so that gives us 5. So this is z squared minus 4z plus 5 equals 0. So what you've effectively done is you found two factors and multiplied them together to get this. So there's two methods to move forward with this, and it really just depends on how you want to work. So the first method would be long division, and this is kind of the obvious one that students would tend to go, oh yeah, I would divide this into here. So we have z cubed, remember k was 8, so minus 8z squared plus 21z minus 20. So that would be our first method. And method 2 will be using the missing factor. So this will be saying, well, if I have z squared minus 4z plus 5, I'll multiply it by z. You can put whatever you want in here. I'm going to put a, and then that should equal z cubed minus 8z squared plus 21z minus 20. So you multiply out the left hand side, which isn't that bad of multiplication, and then you equate. So basically you let the z cubes equal z cubes and so on. So generally the long division method will be the go-to, but some students really struggle with long division. So it's to understand when we could use that missing factor. In algebra, when we have something very similar to this, students always ask, but how do I know which one is easier to use? My answer to that is always, if you know one factor and you're missing 2, then long division is easier, because you'd have to do too much work with the multiplication method. But if you're only missing one factor, then the multiplication method, in my view, is easier. Long division is still absolutely fine, but I find that missing factor, and this, if you want to kind of think of it as missing factor, like singular, when you're missing one, just one. But long division will be more suitable in my view for if we're missing more than one. So if I knew one, and so I think about when we do with cubics, we know one root, we turn it to a factor, we divide it in to get a quadratic. I'm going to work through the two methods now, and you can see which one you prefer. So let's do this long division bit first. So z cubed divided by z squared is z, so that's divide, multiply, so minus 4z squared plus 5z, and then you subtract, so that's minus. They should cancel out, so then this becomes a plus and this becomes a minus. So that gives me minus 4z squared, That's plus 16z, and we bring down that minus 20, and then that divides in minus 4 times. So minus 4z squared plus 16z minus 20, and then these will all cancel out because it should divide in evenly. So therefore z minus 4 is the other factor, and we can then say therefore z equals 4 is the other root. So that means z equals 2 minus 1. We have 2 plus 1 and 4. So these are all the roots. Let me clean up, I think there's a line here, it's hard to see it. So plus I. So that's all of our roots. So if you want to use that missing factor method, we're going to multiply. So we have z cubed minus 4z squared plus 5z plus az squared minus 4az plus 5a equals z cubed minus 8z squared plus 21z minus 20. So we're going to have z cubed terms. So this is our identities or unknown coefficients. So we get z cubed equals z cubed, and that's of no help to us at all. So then we have z squared terms, and we should be able to do it just using one term. So we have minus 4z squared plus az squared, and that should equal minus 8z squared. We can ignore the z squareds, and we get a equals minus 4, and that gives us, you could keep going just to double check it, but we've already done it so we know this is right. So z minus 4 is the other factor, therefore, clean this up a bit, so z equals 4 is the root. So you have z equals 2 minus I, we then have the conjugate, 2 plus I, and z equals 4, and these are all the roots. So that's just a different method to that missing factor method if you prefer. It's really if the long division, if it's not very nice. In this case, it's much of a muchness, but if we had non-real, so as in complex coefficients, that long division would be much more difficult. So I'd suggest this method if we were looking at a similar question, but where the coefficients were complex. Okay, so find minus 1 minus root 3i all under a square root and give your answer in the form a plus bi. So basically we want to write what we currently have as a plus bi. So we can just let that equal, and we're basically going to find an a and b that makes that correct. So to get rid of that big square root, I'm going to square both sides. So a squared plus 2abi plus b squared I squared. So we're going to sub in for that I squared. Square root and the square cancels. That's minus 1 minus root 3i. So we get a squared minus b squared plus 2abi, and that equals minus 1 minus root 3i. So we're going to focus in on the real numbers, and the real numbers give us a squared minus b squared equals minus 1. That's kind of like our first equation. And then if we look at the imaginary parts, we get 2abi is equal to minus root 3i. Ignoring those i's, we get 2ab is equal to minus root 3. So that's our second equation. So we have simultaneous equations, but it's linear, non-linear, so it's a little bit more complex. So what we want to do is isolate one of our terms. I'm going to isolate a. So I'm going to say a is minus root 3 all over 2b. And when I know that, I'm going to sub in, instead of a in equation 1, I'm going to sub in minus root 3 over 2b squared minus b squared equals minus 1. Cleaning that up, we get 3 over 4b squared minus b squared equals minus 1. To get rid of the denominator, I'm going to multiply across by 4b squared, b squared and 4b squared. And that gives us 3 minus 4b to the power of 4 equals minus 4b squared. So I'm going to rearrange this. So 4b to the power of 4 minus 4b squared minus 3 equals 0, because this is a form of quadratic. It might be hard for you to see, so what we can do is let x equal b squared. If you don't have to do that substitution, the substitution just makes it easier. It's because you have a b power of 4, b squared, and then a constant. So actually that's 4x squared minus 4x minus 3 equals 0. You can use minus b if you want. Guide number should work. I'm not going to go through guide number here, but guide number should give us this as an answer. Working that through, we get x equals 3 over 2. And x equals minus a half. So there are two answers. So then what we want to be able to do is work out what b is. So x squared is x is actually b squared. So that gives me b squared, and b squared is equal to minus a half. Now remember, a and b are real numbers. So when I square root this, I'm going to get an error. So my focus is on this one here. So b squared is equal to 3 over 2. I'm just going to clear the screen. So b squared is equal to 3 over 2. Therefore, b is equal to plus or minus square root of 3 over 2. So now that I know b, I can go back to equation 2 and find a. So let's start where b is equal to just root 3 over 2. Then a is minus root 3 all over 2 times root 3 over 2. So it looks something like this. And we should be able to clean that up. So if you're going to put that into the calculator, you're actually going to end up with root 2 over 2. I prefer 1 over root 2 when I work it out. So either of those answers is absolutely fine. And then we can do the second one. So b is equal to minus root 3 over 2. And we get something similar. So this, sorry, now I'll put my 2 in the right place. That's from equation 2 that I'm getting this. Minus root 3 all over 2 minus root 3 over 2, so that's going to end up being positive. So again, you're going to end up with pretty much the same thing. Root 2 over 2 if it's in your calculator, 1 over root 2 otherwise. So that gives us the two numbers are 1 over root 2 minus root 3 over 2i, or 1 minus 1 over root 2, and that is plus root 3 over 2i. They didn't specify into any particular form or anything like that. If you're working in your calculator, the calculator will rationalize the denominator. So what we will end up with is root 2 over 2 minus root 6 over 2i, and it will be the same thing, root 2 over 2. So if you get that, that means exactly the same thing, 2i. In an exam, in a real exam question, I think they'd be a lot more specific about what exactly, what kind of form they wanted it in. but either of those forms are perfect. Question 3. So this is a 20 mark question. I've removed a 5 mark part that would have been at the end. I covered this as one of our examples as we were working through complex numbers. So part A is giving us the complex number z and asks us to write z in polar form. So in order to write something in polar form, we first need to find the modulus, so the distance from the origin. That's given as the square root of the first real part of the complex number squared minus root 3 over 2 squared. So it's a version of Pythagoras, and when we do that, we actually get that equal to 1. The second thing we want to do is figure out the angle. So before we can figure out the angle, we need a little bit of a sketch. So this is the complex number minus a half minus root 3 over 2i. So we have this angle here, which we can call angle A. And the argument, so the full angle we want to use, is this one here, theta. It is possible to use negative angles here. We'll stick to using the positive angles. So first thing I need to do is figure out what A is. To get tan of A, we figure out rise over run. So based off this complex number, that's root 3 over 2, and that's a half. So tan of A is root 3 over 2 divided by a half. That means tan of A is equal to root 3. So A is equal to 60 degrees. In order to work out the argument, so theta, what we're going to do is we're going to say, well, theta is equal to 180 degrees plus 60 degrees. And that means that is 240 degrees. Creating then z in polar form, it's going to be 1 cos of 240 degrees plus I sine 240 degrees, which is just cos 240 degrees plus I sine 240 degrees. If you did those in radians, that would be absolutely perfect. If you worked it with negative angles, because it is closer, because it's over 180 degrees, negative angles would also be okay to use. But we're going to keep it nice and simple and just work with our positive degrees. So part 2, hence find the 4 complex numbers w such that w to the power of 4 equals z. So we're being told that w to the power of 4 equals z. So w is equal to z to the power of a quarter. So we're going to use de Moivre's theorem to figure out these 4 answers. So what we want to do is have z to the power of a quarter. Actually, I'm going to go back a step and actually start with z and then apply the quarter. So when we have z, we have cos of 240 degrees plus I sine 240 degrees. Now, if I come along and I apply a quarter, what's going to happen is I'm going to get one answer, but I actually want 4 answers. So next thing I'm going to do, I'm going to actually find the general polar form. So it's actually a step further than just polar form, and basically it will take into account the fact that rotations will also give us the same answer. So plus some number n times 360 degrees plus I sine 240 plus n times 360 degrees. So this piece, the general, is this plus n times 360, where we're talking about n is a positive whole number. So now what we're going to do, we're going to take z in the general polar form and do it to the power of a quarter. So we get cos of 240 degrees plus n 360 plus I sine 240 plus n 360, and that's all to the power of a quarter. So how that works using de Moivre's theorem, you're going to get 1 to the power of a quarter, which is still 1. And this becomes cos, and you're going to multiply. So it's going to be 240 plus n360 multiplied by a quarter, so that's all over 4, plus I sine 240 degrees plus n360 degrees all over 4. Now, that is only a general solution, so we need to take the general solution and start subbing in for n. We want 4 answers, so we're going to use n equals 0, n equals 1, n equals 2, and n equals 3. So now we have the general formula. We're going to do n equals 0. So our first answer is cos, and you sub in 0 there. So we have 240 plus 0 times 360, but that works out cos of 60 degrees plus I sine 60 degrees. We then do n equals 1. So when you sub in n equals 1, we have 240 plus 360. That'll be divided by 4, and you get cos of 150 degrees plus I sine 150 degrees. We then can do n equals 2. And n equals 2 is going to be 240 plus 2 times 360. And then divide by 4, so that's going to give us cos of 240 degrees plus I sine 240 degrees. And the final one, to get our final answer, is n equals 3. So we have 240 plus 3 times 360, and then divide by 4, and that gives us 330. So you get cos of 330 degrees plus I sine 330 degrees. Now, they're all in polar form, but they've asked us to give that in rectangular form, so we need to basically convert each of those. So here is our first root, and it is a half plus root 3 over 2i. Our second one, minus root 3 over 2 plus a half I. Third one, w is equal to minus a half minus root 3 over 2i. And lastly, w is equal to root 3 over 2 minus a half I. What you might notice at this point is that rotation is happening again because we're talking about power 4. So we're talking about 4 roots. The difference is we would have had to work out that first root anyway, and actually it's just as easy to do the substitution of n1, n2, n3 than it is just to multiply it by I. If you had forgotten to do the general polar form and had only got one answer, you could have used the idea of rotations to finish that off. Question 4, also a 25 mark question. Example 5.3, roots of a complex number. So I have z here, and it's minus root 3 plus I is a complex number where I squared is equal to minus 1. Write z in polar form. So the first thing we're going to do is we're going to get the modulus, and that's the square root of minus root 3 squared plus 1 squared, which is square root of 3 plus 1, which is equal to the square root of 4, which is equal to 2. So that's the modulus. The second thing we want to do, we're going to just sketch that out. So minus root 3 plus I, so it's somewhere over here. Minus root 3 plus I. That means it is 1 up root 3 here. So to figure out that angle there, which we can call A, the tan of the angle A is rise over run. So then our angle here for A works out as, what does our angle work out as? So 1 over root 3. We can do this in either radians, that's pi over 6, or if you prefer degrees, that's 30 degrees. In these questions, there's nothing to indicate which way to work. I would tend to work radians, but to be honest, it doesn't matter unless the question specifies which. It's probably easier to work in degrees for the majority of students. So that's A, but we want to work out theta, so this angle here, so using the unit circle. So theta is going to, I'm going to work radians first. It's 180 degrees, so pi minus pi over 6, which is the same as 180 minus 30. So that gives 150 degrees. Here gives 5 pi over 6, so whichever way you want it. And then bring it back. So the two ways you can write that in polar form is going to be 2 cos of 5 pi over 6 plus I sine 5 pi over 6. That's radians. Or if you prefer degrees, z is equal to 2 cos of 150 degrees plus I sine 150 degrees. So part 2, use de Moivre's theorem to find z to the power of 4, giving your answer in the form a plus bi, so rectangular form. So let's start with z. Again, you can work in radians or degrees. We can have 2 times cos of 150 degrees plus I sine 150 degrees. We want z to the power of 4, so that's this whole thing to the power of 4. How we work to the power of 4 is use our log tables, and it'll give us the rule, and that is you do 2 to the power, and then you have cos of 4 times the angle. So that multiplies the angle plus I sine 4 times 150. So that is what de Moivre's theorem states. We do need to be able to prove de Moivre's theorem. We'll do that in the proof section, but it's really, really handy to work with it. So we get 16 cos, and that gives us 600 degrees plus I sine 600 degrees. Now, I would always think about rotations. Now, this can all be done on your calculator, but while we're doing it as an example, think of it in terms of rotation. 360 degrees is one rotation, so it is rotated and then done something. So here, if I take away one rotation, I'll get the same angle. So that is actually 600 degrees is the same as 240. Sine of 240 degrees, go to the calculator, we put that in. So what we get is 16 times the cos of 240 is minus a half. The sine of 240 is actually minus root 3 over 2, so I'm going to put that minus in the middle. And multiplying that out, that gives us z to the power of 4, actually works out as minus 8 minus I 8 root 3. Not particularly nice looking, but absolutely perfect. They told us that a and b were elements of OR, so the real numbers, and not integers. So we know that that root 3 is absolutely fine. Using the fact that z is one of the roots, or otherwise find the other roots of z to the power of 4. So I'm going to show you a nice little shortcut that works here. Because we're talking about z to the power of 4, it only works with power of 4. But you could, the or otherwise, is talking about using de Moivre's theorem, which we'll see in another example. So the first thing I'm going to do is I'm going to basically get an Argand diagram. And my Argand diagram here has the real axis and my imaginary axis. So we're talking about z to the power of 4. So I'm looking at z first. And z is here, minus root 3 plus I. And what I can do is effectively I can draw a circle so that this circle has a radius equal to the modulus of z. Now, we've already put z in polar form and worked out its modulus, so basically we have a circle with modulus, or with radius equal to 2. Something really interesting happens when you multiply a complex number by I. And when you multiply a complex number by I, it will rotate anti-clockwise 90 degrees. So what effectively happens is, if I took that z and I multiplied it by I, we'd end up down here. Okay, so So that one there is z. So this is iz. And then we'd end up here. So this will be I squared z. And one more. That would be I cubed z. And because we're talking about power of 4, they are the actual 4 roots that we are looking for. So we have z, I squared z, and I cubed z. So it's a really interesting little fact. Like I said, it only works for power 4 because only when we're talking about 4 roots do we divide the 360 degrees into 90-degree rotations. So these are all 90-degree angles. So what that means is to figure out, so root 1, so to figure out each root, so that's minus root 3 plus I, root 2 is going to be I times this, minus root 3 plus I, which is going to be minus I root 3 plus I squared, which is minus 1 minus I root 3, and that makes sense based on where that is. Root 3 is going to be I squared minus root 3 plus I, or you can simply multiply the last root by I, but this gives us minus 1 times minus root 3 plus I, which gives us root 3 minus I, which again makes sense, and the final root, root 4, is I to the power of 3 times minus root 3 plus I. That is minus I minus root 3 plus I, which is equal to I root 3 minus I squared, which gives us minus minus 1, which is 1, plus I root 3. So like I said, we can use de Moivre's theorem to work backwards there, and we're going to do that in the next example, but this is a nice little shortcut. At the bottom of page 34 in your workbook, I do talk about this idea of multiplying it by I, and this sketch here is a nice visual display. So just make sure you're clear that it moves anti-clockwise, which is actually normal movement for angles. So when we talk about angles moving in trigonometry and in complex numbers, we do talk about it moving anti-clockwise. So part B, verify that 2i is the root of this equation and hence find the other root of the equation. We've done a little bit on roots already, so it's important to note that actually, because the numbers that we have in front of z and the constant there at the end, because they're not real, we're not going to have the conjugate root theorem. That's not going to click in here. The verifying isn't going to change. It's going to be pretty much the same as what we always see. So let's power ahead with that, and then we'll take a look at how we'll find the other root. So the root is z equals 2i, just like in algebra, but we're using a z instead of x. To verify that it is a root of the equation, we should be able to sub it in, and when we sub it in, it should balance the equation. So in this case, so 2i, when we sub everything in, it should equal 0. So we just need to verify that that is the case. So we get 4i squared. Be careful now, you can move the 2i in front if you prefer. So we get minus 2i minus 6i squared minus 2 plus 2i equals 0. I'm going to clean this up a little bit. I have a minus 2i and a plus 2i. I have a minus 4, a plus 6, and a minus 2 equals 0, and that is true. 0 equals 0. Therefore, 2i is a root. Okay, so just like we would in algebra or in functions. So if we want to then find the other root, you could use division. If you're going to use division, in this case, it actually isn't so bad because it just has an imaginary part. So I'll just do it here in a different color if you want to. So the root would be z equals 2i. So therefore the factor is z minus 2i, and you would divide that in. The division isn't as bad because it's just 2i as the root rather than a real and an imaginary part, but because there's imaginary numbers in the equation itself, it is a little bit challenging, and I would strongly recommend an alternative method. So what I would be using is z squared, this little shortcut, minus sum of the roots z plus product of the roots. And this is really, really helpful for these kind of questions. So what we have is z squared minus 1 plus 3i z plus minus 2 plus 2i equals 0. So we've actually found the sum of the roots is 1 plus 3i. So my first root is 2i, and when I add that to another root, so let's say the other root is z, we should get 1 plus 3i. So the second root that I'd have to add to it is 1 plus I, and that gives me straight away the second root. So that's the other root of the equation. So this is using the sum. You could use the product, but if you're going to use the product, there's going to be division, and when we divide complex numbers, you're going to have to use the conjugate, and it's just a little bit more complicated. This is the easiest method to work with. In this question, the signs were good for us, so we had a minus in front of the 1 plus 3i. It won't always be the case, but just really highly recommend learning that little shortcut, that z squared minus sum of the roots z plus product of the roots equals 0. Not hugely beneficial in the algebra section, but when we get into these complex number questions, makes life so much easier if we have them. So question 5, this is a full 25 mark question. So there's 4 complex numbers, and using they're shown in the Argand diagram, and the same scale is used on both axes, and that's important. And note where the 1 is, and I'm just going to highlight that because this is kind of the key to the question. So they said, which of the numbers z2, z3, z4 best represents z1 squared? So I'm going to connect up. I always like to connect back to the origin. I think it gives a better sense of the complex number. So there's my z1, and basically I'm trying to figure out what other complex number on that best represents z1 squared. Now, if I think of z1 in polar form, I get or cos theta plus I sine theta. And if I then go and decide to square that, so using de Moivre's theorem, we'd have z1 squared is equal to or squared cos of 2 theta plus I sine of 2 theta. So the modulus is squared and the angle is doubled. So focusing in on maybe just the angle for a second. So my angle is doubled, so I have 2 theta. So if this is my angle here, so let's say that that's theta, 2 theta is going to bring us up this direction. And oh, convenient, there is actually 2 complex numbers that could be. So is it going to be z2 or z4? Now straight away you might say, well, if I'm squaring the modulus, it's going to get bigger, so surely z4. But again, come back to the numbers that I highlighted at the start. That modulus of z1 is actually less than 1. So since, or we can call it 1, well, so the or up here is less than 1, or squared will actually be smaller. So if you think about a half and you square it, a half times a half is a half of a half. It's a quarter. So actually we're looking at a complex number where the modulus actually is smaller. So therefore z2 is the best representation of z1 squared. So the angle gets us so far, but then we really need to be on the ball looking at the diagram, seeing that that modulus is less than 1, because that makes a huge difference. So if you said z4, You're on the right track, but just be very careful with regards to reading the question. So then it says plot the relative positions of IZ1 and Z1 bar, which is the conjugate, and label each point. So this is going to be rough because I'm on the laptop, but you need to measure this out properly. So to do the modulus, to do the conjugate, it's going to be the image of the complex number under axial symmetry. So what that means is it's going to come straight down, that should be perpendicular, and this length should be equal to this length, and you do that with a ruler. It's not a guess. And you should be able to make effectively a little triangle. The next one that they want us to do, which is probably even harder for me to do now without on the screen, is IZ1. So when we multiply a complex number by I, it rotates 90 degrees anti-clockwise. So we end up with something like this. This distance should match this distance, and this should be a right angle. Again, you need to do that properly. Do what I say, not what I do. I can't use a ruler against my screen, but they should be lovely right angles. They should all be measured out. That is IZ1. So we would have talked about this when we did complex numbers, about how that looks like IZ1. So we talked about this multiplying by I rotates it 90 degrees anti-clockwise. So that doesn't need any kind of working out. We don't need any numbers. We don't have any numbers. But we just need to understand how they relate graphically. So this is a nice little question. It is kind of a mix between our division shortcut we have, but also de Moivre's theorem. So there's two different ways you can work it. You can actually manipulate it and use laws of indices, but I'm going to do it I'm going to do it the more obvious way. I'm actually going to apply de Moivre's theorem. So that power of 11, what we get is cos of 11 times pi over 18 plus I sine 11 times pi over 18. So multiply by 11. And then that's all going to be divided by cos of, bring that in, that's 4 pi over 36 plus I sine 4 pi over 36. And we can do a little bit of cleanup. The top line doesn't clean up a lot, but the bottom line does, because 4 cancels, so I'll do a little bit of that. So 4 goes into 36 9 times. And what I'm going to do now that I've done a little bit of cleanup is I'm going to apply our shortcut, and the shortcut is so useful. And we have a shortcut for multiplication and a shortcut for division, and they're the opposites of each other. So if you know one, you'll know the other. So for division, we divide the modulus of the top by the modulus of the bottom, but there is no modulus, which implies that it's 1, so we don't have to work with it. And then we subtract the angles. So the argument, so we get 11 pi over 18, and we're going to subtract pi over 9 plus I sine, and we get 11 pi over 18 minus pi over 9, and we're going to do a little bit of cleanup with that. You could go straight to your calculator at this point, but I am going to do a little bit of cleanup. So we end up with cos, that works out as pi over 2 plus I sine pi over 2, and we do want it to go back to rectangular form, so 0 plus I. So that is a plus bi. The case where it says a plus bi, I will be leaving it with the real and the imaginary part, even if one of them is 0. Unless they just say simplify rather than a plus bi. But when they've specified a plus bi, I think it's important that we give them what they ask for. So the last part of this question then says find two complex numbers x plus yi for which x plus yi squared is equal to w. So we have x plus yi squared, and that should equal w, which for us is 0 plus I. So what we're going to do is we're actually going to multiply or expand out that left hand side. So I'm going to use my shortcut for squaring. So we get x squared plus 2xyi plus y squared I squared, and that should all equal 0 plus I. Cleaning that up a little bit, we get x squared minus y squared when we sub in for I squared plus 2xy I, and that equals 0 plus I. So we can do what we would normally do with our identities in algebra. So we let the real parts equal the real parts. So that gives me an equation. And we'll do the same for the imaginary parts. So in the imaginary parts we have 2xy I equals I. If you're getting rid of the i's, just be careful that that equals 1, because it's 1i, and that gives us equation 2. So we have simultaneous equations. It's a linear, non-linear, so it's not particularly nice, but we can work with it. So I'm going to go back to equation 1, and I get x squared must equal y squared. Now just be careful here. As soon as you apply a square root, we should put a plus and minus square root in front of it. So that means x could equal plus or minus y. So there's two options here. So going to equation 2, let's start with x equals y. So that's 2x, x equals 1. So x squared equals a half. So x is equal to plus or minus the square root of a half. So if it's easier, I would find it a little bit easier to say 1 over square root of 2. So when you have a square root and a fraction underneath, you can apply the square root to the top and to the bottom. So if we were to look at x equals minus y, then we will get 2 times x. I've kind of subbed in the wrong way, but effectively minus x. Or you could do it the opposite way around, the y's, and that would equal 1. But basically what we end up with is minus 2x squared or y squared equals 1. So x squared is equal to minus half. And there's no answer to that because x would equal the square root of negative half, plus and minus. And there is no answer there because we can't get the square root of a negative number. And I know you say, oh, we're in complex numbers. But remember that x and y from up here, x and y both need to be real. So this is not valid. So the two answers are if x equals 1 over root 2, then y will be the same, 1 over root 2. And if x equals minus 1 over root 2, then y will equal minus 1 over root 2. So that two complex numbers are 1 over root 2 plus 1 over root 2i, or minus 1 over root 2 minus 1 over root 2i. So nothing very difficult in that, but a lot of tricky little things. So just keep your eyes open and really think as we're going through these questions. The complex numbers, we often see a little bit of simultaneous equations at the end, and sometimes they're not so nice, or appear not to be so nice. These were quite, not straightforward, straightforward would be the wrong word, but there's no big calculations involved in it. They're not very long. They're quite easy when you've seen them, but they can be tricky. There's a lot of things that could go wrong.